In our previous video, we looked at the multiple server model. That is, we have one long line to wait in, and then as a cashier becomes available or a person who is at the call, so we're calling in for customer service, anyone at the call location becomes available, a service representative becomes available, then you get connected with them. So one queue, and then multiple servers. If we have one queue and multiple servers, then we need to answer the question of how many servers should we have. And so we need to look at the total cost of the servers. So for example, if we have cashiers that cost $15 an hour, so we're paying Alberta minimum wage for the cashiers at $15 per hour, how many cashiers should we have at our grocery store? Well, the more people we have manning the cash registers, the more we're going to be paying in those wages. Okay, so that means the more servers, the higher the serve cost. That's going to pull the total cost up. And that's the second part here, right? The second part is going to be the server cost, that's the CS, and K is going to be the number of servers. So if we have here in our multi-server model, how many of these do we have? Now we trade that against the cost that's associated with the waiting cost. And we have to think about the fact that if we have someone waiting, how much do they typically spend at our grocery store? So if the typical customer pays, buys $35 worth of stuff, then we need to keep them waiting to get their $35. If the wait is too long, they'll give up and leave. And so what we have here on the left part of this calculation for our total cost is the waiting cost. So our waiting cost has $35 per customer. Well, how many of those customers are we going to lose? So we can see here that the longer the wait, the more that is going to make if the waiting cost decreases, if we can make the waiting cost decrease, then that will pull the cost down. And if we're making that waiting cost decrease by having more servers, that's going to pull the serving cost up. So when we look at these two costs, the waiting cost and the serve cost, we want to find the point at which they're at the minimum. So we want to look at that trade-off between the wait is too long and that's costing us customers, and we're paying for servers that are not being used. So let's look at how we would do this in Python. Just a reminder, we are at drstephpowers.github.io/BIA. We are doing the workbook here called simulation. All right. And let's go in to our notebook here. All right, so we are specifying lambda and mu. So just to remind you, when it comes to lambda and mu, lambda is the arrival rate, the average number of arrivals per time period. And in the scenario we've been looking at, we'll start with it at 0.6. So we don't have a person arriving every minute. There's a bigger space between arrivals than a minute here. And we have a service rate, the average number of units served per time period. And so our time period here is in minutes. If our service rate is 0.9, then we're almost serving one person every minute. All right, so we enter that in. The other piece we're going to need is going to be the cost of waiting. So that's going to be the $35 the typical customer would spend. And then the cost of a server, that's how much we are paying for the server. Okay. And then here, K is going to be our number of servers. We'll look at 1, 2, 3, 4, 5, and 6. Okay. Now we're going to start with an empty list, K underscore TC. That's going to be our total cost based on our different number of servers. And what we're going to do is we are going to create our conditional statement, our if-else. So if I is greater than 1, we're going to use our multi-serve function. And if if it's not, if else, so it is 1, then we're going to use our single serve function. Okay, so we're going to give that lambda and the mu, and then we'll give k, which is going to be our number that we're looping through, which is going to be the number of servers. And so we're going to have it output here, our P naught, our LQ, our L, our WQ, our W, our PW for these 2 scenarios. And what we're doing is we need the L from these. Okay. And so just to take you back here, if we look at with the single serve and multi-serve, what we need to calculate here is the average number of units in the system. That's the L. And we're looking at the single serve model, and the L, the average number of units in the system in our multi-serve model. So we need that L formula. Okay, so here's our L. And then our K is going to be the number of our servers. Okay, so let's go in here. And we'll do C underscore W plus C underscore S times whatever K is, and we'll populate that. Okay, and we can show this on a graph. We can import matplotlib.pyplot as PLT to do our graphing. And we can turn this information into a table using pandas. So we have imported pandas as PD. We're using a data frame. We're going to pull that information that is going to be our total cost, and then it's going to have our wait and our serve costs. So the 2 separated, and then we can add them together, or we can add them together. And so we can create this table here. So if we have, oh, that's our index. So we can see the different total cost here, the cost of waiting plus the cost of serving. So you can see initially that we have more of a waiting cost than a serving cost. And then as we get to more servers, then there's more of a server cost than we have the waiting cost. Okay. And we can plot this information using matplotlib. So we'll do plt.plot. We'll plot our total cost. We'll also plot the wait cost and the serve cost. Because as I said, we're looking for the point at which the total cost can be minimized because there's this trade-off between the waiting and the serving. So we are going to create a y-axis that's total cost, x-axis number of servers. We can have our legend right here. We have the names, but we haven't moved it outside of the graph. And so we can do this, and we can see our graph here. So what we see here is that the total cost initially falls as we go from 1 to 2 servers because there's less of a wait time. And then what happens is that as we add more and more servers, it goes up with the cost of those servers. But wait, we actually have an error in our code, right? Because in this, our lambda and our mu were based on per minute. And our cost per server was $15 per hour. So technically, we should be taking 15 and dividing by 60 to get the cost per minute of each server. So when we rerun it that way, what we'll notice here is that because we are able to handle essentially a customer per minute, notice now, as we spread that $15 across the hour, notice that the cost to wait is much more cost prohibitive, right? The longer you make them wait, we're losing that $35 that they would have spent in the 1 minute they could have checked out. And the cost of our server is considerably lower. So when we plot that here, what we see is that the total cost is really highly dependent on the wait cost, and in which case we want to go here with the number of servers being 2 in this case to help us as we look. Well, yeah. It looks like we could add more servers and make the cost go down a little bit. But remember that there's not a lot of wait time once you get past that second or maybe that third server. So maybe we go with 3 servers if our servers are super cheap. And that way no one ever has to wait. And so we're getting that $35 for every minute they're checking out. So here we're looking for the lowest total cost, which technically I guess is 3 servers, where there's not a whole lot of change here. And we're going to have that server be super idle, but the server cost is very low per minute here compared to the waiting cost. Now, what if we paid our servers way more? So what if they were making, let's say, I don't know, $200 an hour? Run that through. Okay, we can see that the cost of waiting is still way bigger than the cost of serving. Here, 2 servers gives us that minimum total cost. At some point, let's say that the typical the typical customer only spends $10. Let's say the servers get paid $300 an hour. Maybe they're providing specialty. Maybe it's not a grocery store. Maybe it is a lawyer, an accountant. Okay, so we can look here in this case, and we can see that after the first scenario here, the server is more expensive than the wait. And so we can then look at that graph here, and you can see total cost minimizes here at the number of servers too. And that in this point, the server cost is way more than the wait cost. So as you're doing this, so what we want to know is we want to know what is the cost of waiting. So if we make them wait, we're not getting their money from their purchase. And we want to know what's the cost of a server. And we do want to make sure it's measured in the same increments. Lambda and mu were measured per minute in this scenario. So we do want to measure the pay per minute as well.